So today, lesson 6, 8M1 lesson 6, we are venturing into the perilous world of proofs. So we will cut right over. We're going to do a proof out of the lesson, and then I'm going to give you a few homework helpers. This should maybe take about 10 to 15 minutes, this lesson. And let's just get going on this. Hopefully I can, again, by the end of this lesson, what I'd like you to do is be at least a little bit more comfortable with proofs. I'd like you to have a list of the proofs that were the building blocks for these proofs, if you will, and also have a little bit of homework help. So let's get going. Here we go. Let's cut over. And so what I'm doing here is we're going to start with, let's just look over here at the right. So what I've given you is something out of the documentation, which is kind of a list of everything that we know to be true so far. And in these things down here are things you kind of prove in some of this we prove in lesson 6. So we can't, the way math works is you start simple and then you build up more and more complicated and complex building blocks. And so the only building blocks that we're going to be able to use are on these proofs, or we're going to be able to use these building blocks here, 1 through 5. 1 through 5, 6 through 7, and number 9. Now, notice that all of these rules really only apply with positive integers, whole numbers. And what's the difference? Positive integers, these are numbers from 1, like 1, 2, 3, 4, dot, 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 dot. Whole numbers are, likewise, 0, 1. So these are positive numbers, and 0, 3, dot, dot, dot. And then here, you basically, well, B can be positive or negative, but all it's saying is that if you have x to the negative 2, that equals 1 over x squared. So these are the things that we can count on, and we're going to prove some of these things. And some of these things say basically, well, all of these rules up here really also, the rules above also apply when exponents are negative. But we have to prove that. That's what lesson 6 is about. We're proving most of these things. So let's start off. And what I want to do is I want to prove what's on, it's exercise 4. And I think this is on page S.23 in the handouts that I have, or S.23. So what we're trying to show is that x to the b power all to the a is equal to x to the ab when a is negative, when a is less than 0 and b is greater than or equal to 0. So we're trying to prove that this rule here, let me use a different color. Let's call this out here. So we're trying to prove that this, which the rule only says is true when m or n is greater than 0, or 0 or greater, that also 11 is true, which is exactly the same thing. But it's true even when a and b are any integer. In all integers a and b, that can be, you know, negative 3, you know, negative 2, negative 1, 0, 1, 2, 3, dot, 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 and also dot, dot, dot in the other direction. So what we're going to try and do is we're going to make this more powerful. And why do we care? Why do we care to prove this at all? Well, I'll show you an example where it's really cool. So if we say that if a is negative, so we can say that x squared to the negative 4 is equal to, well, if we can show number 11 here, then we can just do this multiplication. We could just say x to the 2 times negative 4, or x equals negative 8. We could just multiply these two numbers. But right now we can't do that, because right now what we have to do is there's no rule up above in rules 1 through 9. There's nothing that says we can do this with negative numbers. So above we would have to do x squared to the negative 4. We'd have to then say, well, that's the same thing as 1 over x squared to the 4th by rule number 9. And then we'd have to say, well, that's 1 over x to the 8th by, let's see, that's rule number 2, or rule number 7. And then you could say that that's equal to x to the negative 8 by rule number 9 again. Right? So we want to prove this rule here with negative numbers, so we can just flat out just multiply the numbers and get here, rather than have to go through this 3-step exercise every time. So let's do that proof so we can save ourselves 3 steps per problem. Okay. So the way that they start us off is they say, well, let's just let a equal negative c. Remember, this is the negative number. A is the negative number here. So if a is negative, then we can say that a equals, we can say let a equal negative c. And we know that if a is negative, then c must be positive, because if a was, say, negative 2, then c would be a positive 2. And that's a legitimate thing to say. So now that we do this cool little trick, we can now do some cool substitution, and we can start to prove what we've set out to prove. So x to the b, so we're now going to use substitution. And we're going to say, well, x b to the negative c. So this is equal to this. Those are equal, because I've just done substitution. I've done this cool, this neat assignment trick. Okay, so now if that equals that, then I can say that this is equal to, I can use this rule here. I'll use rule number 9, which says that things to the negative power are that same thing, but to the positive power. And that's rule number 9, right? That says that, you know, x to the negative 2 is equal to 1 over x squared, just like x to the b to the negative c is by definition 1 over this thing here to the positive c power. And now I know that b is positive and c is positive, so now I can come in and utilize this cool rule number 7, because again, m and n are now whole numbers or positive numbers, and so I can use this cool rule that says this is equal to 1 over x to the BC. Now I'm going to stop here on my left side because I know now that x to the BA, x to the B, parentheses to the A, if I do this substitution, ultimately is equal to this down here. Okay, and this is by rule number 7. All right, I got to give, whenever I do proofs, I got to say how I got from one step to the next. Now here I'm going to use the substitution again. Now we're doing right side. And so now I need to make this thing over here equal to, so if the left side, I can make it equal to this thing, and the right side, I can ultimately make equal to this same expression, then I can say that the first two things that I started with must be equal. So let's now do this cool substitution over here and say, well, I know that this is actually have to equal x to the negative CB, right? Because I just substituted A for negative C. Right? Both of these steps were just substitution. Substitution. Right? Now, if x to the negative CB, what can we do? We can now use this cool trick number 9 again. Let's use this trick number 9 and say, well, something to the negative power is just equal to 1 over that thing to the positive power, to flipping the sign. That is very cool. This is number 9, and now things are looking really close. These things are almost the same, but not quite the same. I have to change this thing over here into 1 over x. Well, if C times B is the same thing as B times C, and that is called commutativity. Commutative multiplication. So, in sum, I started here with x to b all to the a, and I was wondering whether that's the same thing as x to the ab. And yeah, I proved this. Basically, I proved that the left side, which becomes equal to 1 over x to the bc, is equal to the right side, which can become 1 over x to the bc power. So I have actually made, using my rules 1 through 9, really combining, rules 7 and 9, I can build and create rule number 11. So let's just look really quickly at a few practical cases of rule number 11 and see how cool this thing is. So I can say, what am I doing? No, I want this thing. I want background of this. Okay, I can say now that, well, x to the 4th to the negative 5 is equal to, well, I don't have to do all this transformation like, 1 over x to the 4th to the 5th, 1 over x to the 20th equals x to the negative 20. I don't have to do this 3-hop thing anymore. I can just say that's x to the negative, what? 20, right? That's just 1 hop because I built a very cool rule. So I want to see you apply it here and tell me now what is a to the 4 to the 3 to the negative 5. What is x, or no, how about 2 to the 3rd to the negative 9, and then 2 to the 1 to the negative x, and then a squared to the negative y. So you can try now, and let's just use our cool new rule that we've developed, and I'm going to give you the answers. So you pause and try, pause plus try. Okay, I'm going to assume you're back. Again, we just use our cool rule that says, x to the a b equals x to the AB. So this is A to the negative 15. This is 2 to the negative 27. This is 2 to the negative x. And this is A to the negative 2y. Box our answers. And now let's cut to our favorite section, which is called the homework help. Some of you may have whizzed through and not worried about any of those proofs, but we want to go to homework help, and I'm going to be working specifically on a problem that's like number 4. So this one's like number 4. And then we're going to do one that's like we'll do one that's like number 7. So the one I want to do for you is I want to show, this is a proof that I want to show that x to the negative 6 times x to the 4th equals x to the negative 2 using only 1 through 9. I can't use these ones. I cannot use. So again, it'd be really cool. I could use number 10. I could show this using number 10 directly. But number 10, because number 10 says I can have my exponents be any integer. But no, I can't do that. Sorry. So we have to show it. So let's first of all say we're gonna do it the long way. Sorry. So we have to basically we have to try and make everything positive and then do our work from there. That's the idea of 1 through 8, and then kind of using number 9 as our trick. Whenever we get a negative exponent, we use number 9 to create a positive exponent and then go forward as far as we can. So let's try and make everything positive. So we're going to start with the left side and see what we can do with the left side. So let's break this in 2. And on the left side, we're going to go, well, we'll make the left side be kind of this color. So we'll go 1 over x to the 6th times x to the 4th over 1. And now what did we do here? What we did here is we basically, to go from here to here, we use rule number 9. Right? Number 9 is our trick to make negatives be positive. Now we simply are going to put these things together. We're going to say, well, this is, x times x times x times x. Or no, let's do it this way. Let's just do, this is x to the 4th over x to the 6th. And this is just, multiplying. Multiply fractions. Now we're going to expand. And I'm going to say, well, that's equal to x times x times x times x all over x times x times x times x times x times x. And now I'm going to cancel. Cancel, 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 1. So this next step was called, expand plus cancel or divide. And now that's equal to 1 over x squared. So we'll stop there. We've shown that this is equal to 1 over x squared, and this is by rule number 9, right? So, or sorry, this is just by the definition. Go 1 over x times x. I go from here to here, and this is really just definition of exponents, right? To say that x times x is equal to x to the 2nd power. Now here, this is just going to be one step. I'm going to go x to the negative 2 is 1 over x squared. And that's, again, by rule number 9. Almost directly, this is rule number 9. X to the negative b is equal to 1 over x to the positive b, or 1 over x to the negative 2 is equal to 1 over x squared. So here we have proved that, or shown that x to the negative 6 times x to the 4th is x to the negative 2. And so this is like problem number 4. And remember, when you're showing this, if these numbers get really, really big, like when we expand here in this step and we have 42 x's, you can just say x to the 42 over, say, x to the 9 is equal to x times x times x. And you could do something like this. Go 42 times. And on the bottom have x times x times x dot 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 9 times. So you can write it out. You don't have to write out 42 x's. Okay, so let's move on one more time to the last problem. So this one's going to be like, again, homework help. Oh, shoot. You know what? I really ought to do this. Let's go back. Let's look at our success here. And let's just drop down, let's just drop down our happy cat. Let's just drop down happy cat right here, because this is a really tricky, tough problem, very involved. We can do happy cat and we can spin him around, and then let's just go back and let's open up this guy. And so this problem here is going to be like number 4. Okay, and so you start off with a problem like this. And I'm going to draw one that's similar, and you're going to say 9 squared times 6 to the 4th over 12 squared. And what does that equal? And it says to use primes. Yeah, the homework wants you to use primes, and you'll see how this works. So we need to basically do a prime factorization on each of these numbers, and then we're going to use our rules over here to then turn around and simplify this expression. And rather than multiply all these things out and then divide them, don't expand, and multiply, using, long division and, tricky multiplication. Watch, we can solve. Don't do that. You could multiply 9 times 9, get 81. 6, and 6 times 6 is 36. Times 6 is 216. Times another 6 is I don't know what. And then multiply all those numbers together and then divide by 144. That's going to be a mess. Watch how we can use our rules of primes to make this a much easier, an easier problem. It's going to be a gentler. It's going to be a gentle problem. We're going to make this gentle, like kind of like butterflies. It's just going to fly down, and watch how cool this is going to be. We'll put a big butterfly here because it's going to be just fluttery, happy. It's going to be the rainbow behind the clouds. This is going to be just beautiful. Okay, so let's get to the math here, and we'll do it in green. So what is 9? If we break 9 down, because it's in parentheses, we don't have to square. We're not going to square this 9. We're just going to say that 9 is equal to 3 times 3. So look at this. So we can say that that's 9 squared is the same thing as 3 times 3 squared. And let's do the same with 6. Break down 6 into its prime factorization. And what is that to the 4th power? Well, 6 is just 2 times 3. 2 times 3. And then on the bottom, 12, if we do a prime factorization of 12, we get 2 times 2 times 3 squared. Now, this is going to be really cool because we're going to now use this rule right here, rule number 8. We're going to use it 3 times to simplify this expression. So this says that if I have a number that's like, 4 times, or let's see, if I have a number like 5 times 7 to the 3rd power, that's the same thing as just 5 to the 3rd power times 7 to the 3rd power. So here, 3 times 3 to the 2nd power is the same thing as 3 to the 2nd power times 3 to the 2nd power. Likewise, 2 times 3 to the 4th power is 2 to the 4th power times 3 to the 4th power. And then below, I get 2 to the 2nd power times 2 to the 2nd power times 3 to the 2nd power. And now what I can do is I can kind of regroup these things on top and bottom. So watch what I do here. So that's the same as 3 to the 2nd times 3 to the 2nd times 3 to the 4th, because I'm using commutative property over times 2 to the 4th. Right? I'm just reordering how I multiply these numbers. On the bottom, I don't need to do that, but I'll just rewrite it. Now let's use this rule. Let's use rule number 1 to simplify this guy. Well, 3 squared times 3 squared times 3 to the 4th is 3 to the 8th times 2 to the 4th. And on the bottom, I have 2 to the 2nd times 2 to the 2nd is 2 to the 4th times 3 to the 2nd. So let's just reorder what's on top here. 2 to the 4th times 3 to the 8th. All that's over 2 to the 4th times 3 squared. Now it's getting very cool. I can just watch what I do here. I'm going to cancel these guys. And then what I'm left with is 3 to the 8th over 3 squared. Well, I can use this rule, rule number 13. Say, well, 3 to the 8th over 3 squared is the same thing as 3 to the 8th minus 2. 3 to the 8 minus 2, and that's 3 to the 6th power. And so we can drop down a happy cat because we are, where's happy cat? Where is happy cat? Uh-oh, happy cat. Come back, happy cat. Happy cat. There he is, happy cat. Spinning happy cat. Okay. And now problem number 4 is a lot like this one. Now remember, all you're going to need to do is, build your prime factors and then use, rule number 8. And then you're going to end up doing some canceling down here at the bottom and coming up with a nice answer. Okay. What I want to ask is, hopefully this was a useful exercise for you. Hopefully this helped out. We did one proof. I gave you a little bit of homework help. It's all about learning those rules, using those rules over and over. Be persistent. And if you have any questions about this lesson or any difficulties, any other homework problems you want help with, post a question, a comment on YouTube, and I can get to that and I can make another video. But for now, we'll just leave it at that. Hopefully you're jamming along, loving exponents, and again, these videos are of use. That's my sole goal, is to be of use and help to you and help you learn algebra, the building block of all mathematics.